We're back live. I got a meeting time wrong. It was Pacific. So I got another 3 hours. A couple things that I want to do here. Okay, so this is interesting. Score gets to just above 0. Let me see why this is. It should get to 1. I did all these experiments, right? And it should get to 1. So let's break out now. So this should be, let's see if I click this one. Is there score here? What this is a synthetic test of carbs, the hyperparam algorithm. So let me see, this gets 991 gamma. It's very close on gamma. 942, so it gets pretty darn close on lambda. Learning rate 002. It's a little bit off. BPT horizon, does it get this? No, it completely fails this. So something is still screwy here. This is not optimizing in the way that we would expect. And you can see here that the total time steps has not been sampled up. So there's this score mod. What about batch size? Batch size is only 32K. Now mini batches is only 2. Up to epochs is 4. Okay. So something is very weird here though, because this should be very easy. This should be very easy for it to learn. And the fact that it isn't learning this implies something about the sampling. I'm trying to think if there's any explanation for this other than carbs being wrong. Right? Mini batches is 2. Like, what is the possible reason? Hold on, this is a uniform, right? I have batches, this is defined as like a uniform. So this should 100% be able to be solved. And it's not working. Let me see why this is the case. So I'm actually going to make a new dashboard, which is going to be a sweep progress. Okay. And this one's going to have different widgets in it. This is all going to be about learning progress over time. So we're going to add some scatters. This will be score. And then this will be start time. Sys creation time. And then the y-axis is going to be score last. Okay, and then we're going to do this for basically for all of these hyperparameters. And then this is going to tell us which of these are improving over time. So yeah, we're going to do okay. Nope. Creation. Yeah. Okay. I think that we're actually going to be able to. We're going to be able to. We're going to be able to actually understand what's going on now, because the synthetic test. This is a very good idea. I should have done this a long time ago. Okay. So we got batch size. No, not score. This is batch size. Train batch size last. Okay. Okay. So we got batch size. And then we got now mini batches. We only have to do this once, and then we'll have this dashboard for usage. Okay, so here's this. I don't know why there's this huge gap in the creation times, but whatever. We do gamma. Lambda. Okay, add this. Why is this the same plot? Because they're just very similar. Okay. And then update epoch. So what this shows you, this doesn't show you performance, right? This just shows you the hyperparams. This shows you how your hyperparam sweep algorithm is changing over time. BPTT. And I think this is it. Okay, so now we have all of these parameters. I don't know what's up with this. This might be from like a partial sweep or something. Something weird. Also, this is... Yeah, that's kind of weird. Also, this only gives you 200 runs. Okay, I think that the thing is this is not giving us the right 200 runs that we want. So let's do none. And then, well, why did that just change a whole bunch? Hold on. 10, 14, or 223. Okay, so yeah, what's happening is it's showing us the most recent runs. And that's a really bad thing to have in their UI. So 422 items. So we actually want the first 200 of these. I see. I'm actually just going to do, this doesn't take very long. And I'm going to change the max runs because this is very awkward. This should be 200. But that's such a bad UI thing, the way that they do that. So we're going to do this. I want to see what this does. This will give us a very different picture, I think. Neptune unsupported type. Hang on. Oh, that's fine. These are just parameters. Cool. So now this is running. And this will run very quickly. Now, we know that it didn't full solve. We did not fully solve this, even by the end. We might get some progress over time curves, but we know this is not going to full solve. And then the question is going to be why. So in the meantime, while this runs, I want to look at the way that carbs samples its parameters. Because I suspect it's not doing what we want. So we get suggestion output, get random suggestion. This is generate candidate. Okay, so dot fit, and then you fit the suggestions, you fit the failures, fit Pareto set, and then it generates candidates, num samples to generate. Samples in basic. So you get sample around origins in basic. Okay, so this surrogate model gets fit, but then you sample around the origins, and you round this. Well, where's the surrogate model? Where does this get used? This is what I don't understand. I don't understand how they're generating their suggestion. So is expected biasing technique so what do you actually return from this? Oh man, you returned, okay, there's a lot of stuff. So samples in basic of best index. Ooh. Oh, shit. Is that what they're doing? Okay, I think I see why this is wrong. Yeah, okay, I see why this is wrong. So it looks to me, and I gotta check the carbs paper, but do you see this? So they generate a whole bunch of random samples based on the space definition that you provide. So it's only going to sample according to the initial distribution that you provide. And then they use hold on. What do they call the surrogate model? Surrogate output. Acquisition function value. I think that what this does is it's using the acquisition functions to rank the suggestions. And then it's only giving you the best ranked random suggestion. It is not actually giving you a new suggestion. This would make sense because this is why carbs is supposed to be able to generate longer and longer runs over time, but under this structure it will not do that. This seems like a fundamental problem with carbs. I wonder if this is in their paper. How's it going? Cool. So this will progress for a bit. The paper is very hard to read. This is a major limitation with carbs, if I'm correct. Where's the paper? Okay. So, algorithm. Generate candidates in local search space. We define the search space. It's supposed to be Gaussian around the Pareto front. Once we have the candidate suggestions, we estimate, okay, so they are ranking. But they say they defines local search space around points on the observed cost performance Pareto front. So this would be very smart. But I don't think this is what's happening. Does this match the code? Let me see. So they're going to fit the success observations. They fit the failures. They fit the Pareto set, okay? Now, when they sample, they get this samples in BASIC. Oh, but look, the origins in BASIC are the Pareto groups. Sample around origins in BASIC, okay. Origin index. Real samples. Search distribution in basic.sample. Basic. Search radius in basic. In basic. Immediately overwritten. So I think I'm going to have to put some breakpoints in here to figure this out, because this is very, very odd. The thing that they say they're doing on paper makes sense to me, but based on the experiments, I'm not seeing the algorithm do the thing it's supposed to be doing on paper. What it's supposed to be doing is it's supposed to be computing a Pareto front of cost and performance. So it's trying to find runs for which there's no run that is both faster and better. And then based on the Pareto front, it's supposed to sample new points. So that means that if you start off with a slow run, a fast run, you can sample a faster run and a faster run and a faster run, as long as they're on the Pareto front. But this doesn't seem to be happening even with the most basic of synthetic tests. CARB seems to do a very good job just as a hyperparameter tuning algorithm without the cost awareness. That's the important piece, and it doesn't seem to work. Okay, so look at this. So we get up to batch size being decreased is interesting. Let me see. Maybe it's just that it doesn't matter. Okay, so right here, this is what we have. We got our test function. And we get a score mod, which is batch size divided by square root. Am I stupid, or isn't bigger batch size better here? Something is wrong. Bigger batch size should be better here. Mini batches should be better. Everything here should be better. Oh, but it's a multiple. I see, it's a multiple. Okay. Well, that's an interesting interaction. Because the score is negative, you see, right? The score is negative here. It's learning that batch size is a bad thing. I wonder if it recovers from this, because now it's getting positive. Still not getting positive scores. Interesting. It should be getting positive scores. They're all still negative. Yeah, so you can actually see that it's totally messed up the mod parameters. But let's ignore that for a second. Let's see if it's getting the correct values over here. So learning rate, 002. So learning rate doesn't seem to get all the way to where it needs to be. Gamma of 0.99 is basically, this is spot on, right? This is very quickly correct. And then lambda of 0.95 is also, there's a little bit of noise here, but this is correct. It's 0.95. Update epochs. Okay, that parameter is not going to be good. And then BPT horizon. BPT horizon is also wrong. And actually, there's no reason for BPT horizon to be wrong, right? So abs, this minus 16. Yeah, it should be 16 here, strictly. So I suspect that my POW2 spaces are not correct. There are probably two separate issues here. Yeah, and now you can see it's starting to get positive values. Okay, so this score mod here is, I don't think it's ever, yeah, this is just a poorly defined score mod. I'm gonna add 20 here, and that's gonna fix part of it. So that's gonna fix the score mod, essentially making the score worse if it's negative. Because what's happened here is that because the score is negative and then this is a multiplier, it's trying to reduce this multiplier as much as possible. So that's just me screwing this up. Like, that's just a bad function on my part. So let's see what it does from here. I'm going to check a couple things in the meantime. A couple of academic collabs. Give an update later today. Cool. Nothing from this. Nothing from them. Okay, I don't know what they're on about, but whatever. Okay. 11 items. Scores going up. I believe, let's see, there are 1, 2, 3, 4, 5, 6, 7, 8. So yeah, the first like 8 trials or whatever are random, and then very quickly it should start learning more stuff here. Yeah, gamma's already starting to fit, lambda's already starting to fit. Learning rate is not really fitting yet. Let me check some stuff here. So learning rate is 0.005. Okay, so the center param, this is just where it's centered. It should very easily get to 0.001 though. That's within 1 standard deviation. So maybe it just takes a few more trials. But that should be fairly easy to learn. Okay, so here we go. Score continues to improve. Total time steps is still being decreased. I believe I have this as a... Do I have this as a log 2? Mini batches is correct now. Look at this. So mini batches is now correct. Batch size does not seem to be correct. Gamma is getting correct. Learning rate is not... Oh no, it is dropping. It's just taking a second. Okay. Lambda, okay, 0.95. This is what we want. Update epochs is good. So BPT horizon is clearly wrong. And total time steps is clearly wrong. Let's see. Let's look at this. So POW2. So num_ems is a POW2. Let's add ems. I don't think I have this one, do I? Yeah, I don't have this yet. X-axis is going to be creation time. Then y-axis is going to be num_ems. Okay. And I don't actually know I have to have this in the score function. Let me see. So we have num_ems. Not in the score function. So this is allowed to drift wherever it wants because we're not currently using it in the score function. So we ignore this one for now. But now if we look at BPT horizon, it's uniform POW2. Num mini batches is a uniform POW2. And it's only at 4, it's not at 8 yet. Okay. And total time steps is log normal. You know, log normal should work because I use log normal for everything else. So I'm a little confused as to why total time steps doesn't work. Unless I messed up the function. Hold on. Okay, so I can see uniform POW2 being broken. Like that's, we'll look at that, but the log shouldn't be broken. How am I using this in the function? Log 2 of total time steps. You increase this, you increase your score mod. Right? You increase this, you increase your score mod. Score cost. Score cost, yeah. So that is bizarre. Especially, like, we see so many of these are correct. Okay, look at this. So score has gone up to 70. Total time steps is totally crashed. Mini batches has gotten up to 4 and then got stuck. batch size has gotten to 65K and then stuck. Learning rate is still progressing, it looks like. I don't know why it's taking it this long to sample. Lower learning rates. This should be very easy to learn, but it is learning. And then gamma is 9.9, so it's getting up to 0.99. This is very slow, though. It's very slow. Keep in mind, this is a synthetic test with perfect feedback. There is no noise in the evaluations. Like, you should basically be able to do this in, I would guess, 10 or 20 samples. Okay, so lambda actually works very nicely. It kind of does some, like, these are random, and then it hones in, and you get 0.95. MEMS is random, BPT horizon is wrong. Use the restroom real quick while this finishes some runs, and then we'll stop this. I will make sure I'm completely right about the evaluation function, and then we'll see what carbs is doing, because this is very weird. Okay. We got 48 items. We'll get 50 points from them. Let's see. Yeah, so score does keep improving. These points down here are very weird to me. And this is something that carbs consistently does, is it just misses. Oh, okay, maybe we actually do let this run a little longer, because look at total time steps. It's coming back. But, like, why did it go down in the first place? Right? So we'll let this run a little longer. Not this one. Where's carbs? So many papers. Okay, here it is. So I would love to get somebody to just simplify this whole carbs this whole carbs repository, like really clean this up. It's just way too complicated right now. That actually would be a really nice, like, mostly science side, little bit engineering side contribution. Because it requires you to understand the algorithm. $340. See, they say that this actually does work, and that this will continue to find longer and longer runs. Cost hours. But we're not seeing this working in practice. Okay, this is bizarre. So gamma got to 0.99 here. I don't know why it took that long, though, for it to sample up to here. And, like, lambda is the right spot, but it's not a tight... It hasn't really gotten that parameter tight yet. I also don't know why num_ems would drift down like this, because it's not included in the function. Having drift like this in your... Having this type of drift is very bad. Doesn't seem like this is going way back up. Okay, I think I'm gonna, in a separate window, I'm going to start trying to figure out what the heck is up with carbs. Yeah. Ooh. This is a big repo that I think you could probably clean this up to be like a 500 line repository. Okay, so where's our suggestion? Generate candidates. Sample around origins in basic. Yeah. Let's do the window. Heck. Oh, am I on the other machine? We do a demo or a blade. Okay, so we have here origin samples. let's figure out the order that these are passed in. We'll do flat spaces. Right. Okay, cool. So we've got origin samples. So I can see right here 1.06, and then this log space is at 32. So these have been transformed already. Real samples, tensor, plus search distribution in basic. Search distribution in basic. Normal with a scale of 0.3. So they're transforming my parameters. And then they're using a fixed search distribution in basic. So what do we do? So it's self.search radius in basic, immediately overwritten by set search center. Set search center. Really? Search center. So you set the search center. Param dict type. Search center basic. So search center in basic is very different. Search distribution in basic. Search radius. So this is immediately overwritten by set search center. Which is not true because this doesn't set that. It only sets this, it doesn't set the search radius. So search radius in basic is not overwritten. I mean, I do think that this is worth investing substantial time into because this seems like a very good algorithm that's being held back. So where's search center in basic? We do let's do breaking up here. Okay, so you have param here, and the search center for these is not what it's looking like here. Set param space real to per basic param space real 2. Param space real 2 basic space real. Okay, so dim dot basic from param. Oops. Terminal. Uh-oh. Internet might be dropping. I think we're good. I think just a small spike. I have had some janky driver issues. I'm hoping that they're fixed, but we will see. Basic. We got input in param. And we get, these are the search centers. These are the raw search centers. Okay? And then we do basic from param and self.real input in param. Okay, dim in self.real number space by name. Number space by name underscore. Internet. Oh. Dim.basic from param. Okay, so it's, so the spaces have a function called basic from param. Okay. Value over scale. So this tells you this is the transform, right? It's incredibly confusing. I think basic from param, it takes the raw value and it transforms it to be in a better space for sampling. But the way it's doing that at the moment is not good. Yeah. Because I think what they're doing at the moment, so here they're just dividing the parameter by whatever scale you give it. They're just dividing the parameter by whatever scale that you give it. And then when you sample this parameter, This is why they have a 3 there, because their default sample range is 0.3. So what happens is they divide by the scale that you give it, and then they sample a normal with a standard deviation of 0.3, and then they transform back. So like one standard deviation, right? Let's say that you have 1 to 10, and you give it a scale of 3. Okay, so then you give it a 5. A 5 is or let's make it easier, a 6. So they do 6 divided by 3 is 2. And then you sample with a 0.3 norm. So let's say 1 standard deviation. You sample a 2.3, and then you multiply back, and then that gives you a 6.9, which is a terrible way of sampling. Yeah, that makes absolutely no sense. And this would explain why their algorithm doesn't sample or doesn't explore various spaces in a way that looks reasonable to me. So this is a really, really good algorithm that's being held back by space transformations. So I've just run 119 experiments. It's kind of starting to learn to restore total time steps. It's got gamma, doesn't even have learning rate, really. Oh, it's supposed to be 001. It's a little bit off. It's like kind of getting there. I think the algorithm is really, really good, and like there's not much I can even change with it. It's like a really smart algorithm. It's just this space transformation stuff. So I think I found that out. Is there a chance that I'm wrong here? I think I have it. And I think this is what their paper says as well. Let me see. If it matches the paper, then I think we're good. And then we'll know what we need to change. This will take like a couple days of work probably to fix this, but then we'll be set. Assume that this we define input parameters and outputs are scaled to be of order 1, but they don't actually do this. Local search space around points. We define the search space as a set of Gaussian distributions of radius search around these parameters, defining the unnormalized probability density. So I don't even think that this makes sense if, yeah, this doesn't even make sense if you transform correctly, because each of these parameters should have its own search radius. Because like you know which parameters have scale over many ranges, like many orders of magnitude, and which ones don't. Once we have evaluated the candidate suggestions, 3 Gaussian processes. to predict the performance of a candidate, to predict the cost, and to predict the optimal performance corresponding to that cost, informed only by the Pareto front. Modeling the shape. Okay. I think I'm really starting to understand this algorithm. This is a very heavy algorithm. I'm starting to get it. Using only observations that belong in the Pareto front. Is used as a baseline, the expected improvement. I don't know about this. I'm going to have to get way deep into the code to figure out what they're doing. Box transform. Quantile transform. So they do have some transforms in here. But I think that the thing is that they're applying the transform to bad data. Well, the good thing is that I have this baseline now, right? So I have this baseline. This is how well it does. Let me compute the optimal performance real quick. What's optimal on this? Why can't I set this? I'll just do it here. And then we're going to do something else. Yeah, so this should be the optimal parameter settings. Breakpoint. Yeah, so like you can see here that there are parameters that get 254, way higher. So this means carbs is not actually working perfectly, and optimal params. Carbs is not working perfectly, and we will definitely look at that. So this is why everything's been janked, basically. If we can fix this, then we should have really solid sweeps, and we should be in a really solid position going forward. Okay, that's good for this segment of work. I think the next thing we're gonna do, whoops, let me see. The next thing we're gonna do Oh, interesting. Apparently newer compilers are faster. Cool. General. Let me find this real quick for us. Okay, I'm going to be reviewing this paper now. Minchi paper. Roberta Tim. Okay, cool. This should be good. Elliptical episodic bonuses. Okay. Proposed to explore complex environments. Yeah, we're going to do this review now. Let me get into paper review mode. I'm going to actually make a new scene for this. Review. Add. I should actually flip this one as well. There we go. Oh, I have this because of the mic, I guess. All right, we'll flip this back. Just Test. Test. Audio works here. Does audio not work on the other scene? Okay. I think I have audio here now. Let me go double check from the stream. Let me make sure this works. Does this work? Test, does this work? Yes, okay, it does. Good. Okay, now we have our paper review scene. Paper and code review. Good. Okay, so recent years, RL methods have been proposed to explore complex environments that differ across episodes. In this work, we show that the effectiveness of these methods critically relies on a count-based episodic term in their exploration bonus. Okay, that entire line of work on count-based bonus is a bad idea. That's a ridiculous thing to be doing. So they extend it here. Extend count-based episodic bonus to continuous state spaces and encourages an agent to explore states that are diverse under a learned embedding within each episode. This embedding is learned using an inverse dynamics model in order to capture controllable aspects of the environment. Method sets a new state-of-the-art across 16 challenging tasks from mini-hack suite without requiring task-specific inductive biases. EB3B also matches existing methods on sparse reward pixel-based VisDoom, outperforms existing method and reward for exploration on habitat, demonstrating it can scale to high-dimensional pixel-based observations and realistic environments. Okay. Intro here. Got R&D, ICM, pseudo counts. Designed for singleton RL tasks. The agent is spawned in the same environment every episode. Okay, that's not entirely true. But yes, these methods are pretty limited. Number of methods have been proposed which have shown promising performance in PCG. Okay, this is funny because procedurally generated environments are often easier than fixed environments. It helps. It's called domain randomization. It's a natural curriculum. So this is kind of funny. Surprisingly, count-based often includes the heuristic is in fact essential. Current methods fail if it's omitted, okay. Existing methods fail in more complex tasks. Sure. We're not reading this. Exploration bonuses. That's just needless formalism. Environment rewards are sparse. Learning a policy using simple epsilon greedy exploration may require intractably many samples. Yes. Do I remember liking this paper? Forgot the details? Yeah, we're looking at this now for some stuff, Ryan. Welcome to the code review setup, or the paper and code review setup. Oh, also, we found some screwy things with carbs. So I think we're going to be able to make hyperparam search for RL way better over the next week. Spending a couple hours on this, though. Consider methods that augment the external reward function R with an intrinsic reward bonus B. Number of intrinsic bonuses that encourage exploration in singleton proposed, including pseudo-counts, ICM, R&D, okay? If you make that easy, you're a hero and never do anything besides manual. Okay, Ryan, like you're throwing away 99% of your compute. This has kind of been the conclusion lately. I've been realizing over the last few days, so people throw away 100x to 1000x compute off of using slow environments, but then they actually throw away another 100x compute on bad hyperparam search. So literally all of RL is running at like 1/10,000th of the speed that it should be, and we wonder why nothing works. It's that bad. I mean, it's like the more that I dig, the more stuff I find. And it's like, it's not even like RL is just a hard thing. It's literally just that we've screwed up the engineering at every possible level. These methods define an intrinsic reward bonus that is high if the current state is different from the previous states visited by the agent, and low if it is similar according to some measure. Okay, so they all have some distance measure over states. More recently, several methods have been proposed for and evaluated on procedurally generated MDPs. I'll use different exploration bonuses. Summarized in table 1. Bonus based on distance between the embeddings. Second R&D bonuses. Okay, so basically we want to try one of these that is simple and doesn't make a mess out of all your learning code, and we want to see if it does anything. Importance and limitations of count-based exploration bonuses. 3 methods with and without the respective count-based episodic terms on one of the mini-grid environments used in prior work. Mini-grid N10S10V0. What is this? Does anybody know what this is? N10S10V0. Yeah, but what is this environment? What is it? I can't see the environment to see if this is actually interesting. Is this built in? Can I like go render it? Okay, what is this environment? I can't find it, but the thing that I'm concerned here with is this axis is 1E7. 1E7 is nothing. This is 10 seconds of learning if your library doesn't suck. So, like, if you look at it that way, this is a 10-second experiment. Like, oh, look, no episodic counts, you don't make progress. Most of these problems you can literally brute force with PPO. Fair enough, though. Yeah, you add episodic counts, and it learns way faster because obviously it does, and because that's like a thing you can do with grid environments. Fine. Because like the problem is fundamentally intractable, right? Without a ton of samples, without this like exploration thing. It looks like a ridiculously deep exponential search space. Seeds. If each state is unique, then that will always be one, and the episode. Okay, yes. So you need some sort of encoding over the observation, not just the state. Relevant features from each state and feed them to count-based. Well, this still doesn't make sense, really, unless you have a good discretization. Gotta drop C around, Ryan. Figure 2 shows results on 2 tasks from the mini-hack suite with 3 novel D variants. Trying to outperform standard formulation. It's a bonus. Decisional feature encoding and episode bonus. Okay. It's X and Y. Failed to enables to sell multi-room. Zone freeze. Okay. Cool. In this section, we describe exploration via elliptical episode bonuses. We'd like an episode bonus that can be used in continuous state representations. We'd like a representation learning method that only captures information about the environment that is relevant for the task at hand. First requirement is meant by using an elliptical bonus, whatever that means. Continuous analog to counts-based bonus. We'll see how. Second requirement is met by using a representation learned with an inverse dynamics model. Elliptical bonus. Given a feature encoding, the elliptical episode bonus is described as follows. What the hell? How do you get 1E7 steps in 10 seconds? That would take me like an hour. RMs are fast. So this is why Puffer is awesome, right? All of these environments run at 1,000,000 steps per second on a single CPU core. And most of them train between 300,000 and like 1.2 million steps per second on one GPU. And these range from very simple to some of the most complicated RL environments out there. Like we can train neural MMO3 at about 500,000 steps per second. This is a massively multi-agent open world environment with economy and trade and all sorts of stuff. What's Puffer? Puffer is the library that I am developing to fix the gigantic mess that reinforcement learning is in at the moment. You can check it out at puffer.ai. GitHub is right here. It's all free and open source. Start to help us out a bunch. And we've got a nice Discord community of people building high-performance RLMs, and we're starting to now use those high-perf RLMs to run thousands and thousands of experiments to fix all the other problems around RL, because we can do that now since they're fast. So yeah, this is pretty much what I do. It's like I just stream all of my work on PufferLib, which includes developing and merging environments. It includes doing science-side work on top of our environments. It includes doing some support stuff for clients, adding specific features to PufferLib that people need for both like companies and academic labs. It's just generally, this is my effort to try to fix the mess that reinforcement learning is in, where everything is kind of cursed and hard to make to work. We got classic ones too, simple Pong. These are neural nets. These are trained agents running in your browser as well. Multi-agent snake, lots of stuff. What is this elliptical episode bonus? So feature encoding, I assume, is just going to be like the hidden state. And then what is this matrix? So this is a wait. Is this an outer product? This is. How easy is it to import my own environment like a simple imported inverted pendulum? We have wrappers for gymnasium environments and for petting zoo environments. You will immediately get a performance speed up out of our CPU vectorization on those because our vectorization is much faster than what everything else that is out there. For the maximum performance, you're going to want to look at our native API and our native M's. But if you just want like out of the box, get some good performance speed ups, get like nice hyperparameter sweeps, get RL working generally, then it's very, very easy. And we have lots and lots of examples. Basically anything in the PufferLib environments folder, like any of like the main environments that are actually used actively, you can see how we bind. It's like a one-line wrapper. Pretty much Puffer will give you the best performance for the level of engineering effort that you want to put in. If you just want to wrap an existing environment, that's fine. If you want to do a little bit more work, you know, you can get faster, and it goes all the way up to 1,000,000 steps per second training. Okay, so this formulation bothers me a lot because, well, hold on, I guess, nice, I'll give the wrapper a try, yeah. And I mean, this is why I stream as well. If you run into any trouble, I'm right here, right? Paste errors, I help fix. Okay, maybe this isn't that bad because you can cap this, right? So this is a sum. Wait, I equals 1 to t minus 1. Given a feature encoding at each time step. Is this over the entire episode? So regularization term to make sure that it's not singular. But that's not a good way of making a matrix not singular. And it's an outer product. Okay, so this is a kind of crazy function to include. It's a kind of a crazy function. I guess technically, you can like pass this as an extra state variable, I guess. You can technically pass this as an extra state variable. Yeah. You have to reset this thing though, don't you? Can I decay it over time? I wonder if I could modify this to decay over time. And wait, do you differentiate through this thing? intrinsic rewards. I think that if this is just the reward, you don't differentiate through this, right? Natural generalization of a count-based episode. I have no idea how. Problem is tabular. And this is a one-hot encoding of state. And this will be a diagonal matrix whose entries contain the counts corresponding to each state encountered in the episode. What? CT-1. Oh. That's kind of wonky. Inverse will also be a diagonal matrix whose entries are inverse state visitation counts, which of the entry corresponding, yielding a bonus of, okay. Yeah, so these are some fancy math people did some fancy math. Okay, I kind of see how this works. For a more general geometric interpretation, if they're roughly centered at 0, unnormalized covariance matrix. What the heck? So now consider the eigendecomposition. Okay. Set of coordinates, we can write the elliptical bonus. Okay, I have no idea, honestly. Like, this is, I don't know what the hell any of this is, but okay. Efficient computation. The matrix needs to be inverted at each step. Operation that's cubic. We use the Sherman-Morrison matrix identity to perform fast rank 1 updates in quadratic time. CT-1. Jeez. Okay. Learned feature encoder. Any feature learning method could in principle be used. Here we use the inverse dynamics model approach in 52 to model G along with phi to map each pair of consecutive embeddings to a distribution over actions, AT, linking them, separate from the policy network. Model is chained jointly the following per sample loss. So you take this buffer, jeez, okay. Sample action, step through environment, compute bonus, update covariance matrix. From policy gradient update using rewards, update to minimize the loss. Okay. Torch Beast, Impala, so yeah, terrible library, and then they just do ours. And then they do well. Cool. Mini hack is not a very competitive benchmark because not enough people use it. Impala. 3B. They underperform this. Blue one. Or green one. This. Okay. This is cool. That's a good result. Again, these are not very competitive benchmarks because they're like 5 people doing this work. Different, okay. Different algorithmic components. Whereas a randomly initialized network. This is bad, okay. Policy encode indicates when these weights are tied to those of the policy network, with the last layer producing action probabilities removed. So instead of doing the inverse dynamics model, this is actually way simpler, and that looks pretty decent. Elliptical bonus is computed using observation across all time steps and not just the current episode. Elliptical bonus is computed using observations. Yeah, so that matrix just gets too much junk in it, I guess. Can you just, I think I want to do an exponential decaying thing. Wait, this highlights both the index and the episodic bonus. Well, this is pretty good. The policy encode version is pretty good and it's simpler, right? Mini hack ablations. Yeah, this is pretty good right here. For not having to train a whole inverse dynamics model, I actually like this one more here. What did they get? Say 0.6. And then, yeah, so this is still better than the other methods. This should still be better than the other methods using without the inverse dynamics model, and it's much simpler. So that's kind of what I want to try. Red hook. What's this? That's funny. We got any appendix? Yeah, useless checklist. They had this already, I think. All these NERPs checklists and statements are just so dumb. Follow this 5-layer conf from, okay. It's a big policy for RL. Use Impala, hyperparameters. We did not kneel. rolling normalization, deviation. So they just tuned their new hyperparameters. Yeah, so you can see that they didn't, these are just some parameters somebody came up with. Okay. So they could do way better just by tuning this stuff, but the RL's too slow. Okay. Oh, they do tune. They don't really tune. I guess they did a little bit of sweep, but not really. They did like a dumb grid search. That's fine. Okay, neither baseline. Okay. Well, I'm not going to be too hard on them. Like, the results aren't going to be good because they're slow. So it's fine. GP100, what the heck? 10 and 30 hours. Yuck. E3B was 1.5 to 2 times slower. Additional forward pass through the embedding network used to compute the elliptical bonus was performed on CPU. Why? Okay. Did they release code? Okay, so they do actually tune a little bit. Not great tuning, but they tune a little bit. Habitat details. Yeah. Code base used. Official. Okay, well, where's your code base? Yeah, so I'm pretty sure we solved most of these problems in Puffer, just like with tuned hyperparameters and more samples and training fast. But fine, we'll look at this. So covariance regularizer. Okay. Robust. Do they release code? They do. Good. Good job. It was published in 2020. Oh, 2022. Okay, so 3 years. Cool. Is there anything more recent than this, or is this the best thing? I don't know, maybe, let me just real quick. Good job. You reported older papers. Stupid. Jippity not smart. Okay, let's see code. I'm expecting this to be horrifying if this is built on Torch Beast and stuff. Okay, wait, we got it in Sample Factory. Mini hack / sample factory. Okay. This is 10 times faster than before. 10K FPS is 10 times faster than before. That is horrifying. Holy hell. Good job, Alexei. They do have the sweep here. Is this just vendored? Yeah, this is vendored sample factory. So where is this? Where the heck is this? I love it when the code base is structured such that you can't even find the code in the code base. E3b.py, anybody? No? No E3b.py? Dude, how? Where is the code? Do I have to look at the other one because of how ridiculous this is? They still have a bajillion. Dude, this should be a paper that is like 300 lines of code on top of a standard implementation. I do not know what the hell. Maybe this? Okay, hold on. Source. Losses. Okay. Is this? Okay, here's your inverse dynamics. Cool. And then e3b.py. Elliptical encoder. I honestly have no idea how I've stayed in RL this long. Because like I remember having to deal with stuff like this, and it's just a miserable time. It's just an absolutely miserable time having to deal with libraries like this. They have a separate optimizer for the encoder. Is it? 52. Dot share memory. What is that? Okay, so here's the actual learn function. So that's obscene. Oh, maybe, okay, this is just setting the mode. Okay, right? Yeah, this is, please tell me, this should just be setting the mode. And then elliptical encoder. State embed all. Reward is batch or reward. vtrace returns. Baseline loss. Returns. Yeah, man, I know. This code is like, I literally don't understand. Like, literally, you work on this code base for a week, you'll have crippling depression. There's no way around it. Like, I remember when working in RL sucked this much in the first few years of my PhD, and it was a miserable time. Like, I honestly don't know how I stayed in this field for this long to, like, actually get to the point where stuff doesn't suck. Because, like, it's actually just miserable working on code like this. This is the thing with Puffer. It's like, stuff's actually easy and makes sense now. It's kind of funny, like, I started thinking, like, the stuff I'm doing with Puffer's kind of simple, actually. And then, like, I go look at what everyone else is doing, and I was like, oh my gosh, okay, yeah, no, we're doing good work here. I have some weird Puffer issues to ask about. Have you tested it with slow multi-agent M's? Yeah, it should work. That should work. If you link me a thing, I will take a look at it gladly. Slow multi-agent M's with like petting to wrapper or whatever, you should just like double buffer sample on all the cores. And you should get close to num core speed up. Sure. What M specifically are you messing with? Equal speed with zero. That sucks. No, Puffer should be way faster. Ridley laser tag env. Ridley has its own internal vectorization though, Ryan, right? Doesn't Gridley have its own internal vectorization? I don't know, I'm using puffers. Okay. I can look at it. I know Gridley has really obnoxiously slow resets, so you actually have to be pretty careful with your async. But yeah, if you have, because I know that our Gridley binding is out of date. So if you just want to like PR version of Gridley that actually works, then I will be more than happy to, run the perf test on whatever env you're playing with. Puffer should be fast. Look into more, yeah. I mean, you don't have to narrow down the issue. All you got to do is PR or like branch or whatever, a version like that I can just run, right, and see it. So either like link me your, if you have a fork of Puffer or whatever, Ideally, if you're using Gridley and you actually have it working with Puffer, it would be nice to have that PR'd, because I haven't had the time to mess with Gridley, and Gridley's pretty cool. Like, we have a binding for Gridley, it just doesn't, I don't think it works, because Gridley's kind of weird. They don't define the observation spaces until you reset the env, and that kind of screws some stuff up. Technically not able to share. Really? Oh. Yeah, okay. Well, if we want to do something privately, we can. That's, I don't know why people do that on academic research. That should just be published by now, but wait, is it not a built-in Gridley env? Is that not like a built-in Gridley env? Okay, so it is a custom env. Well, I don't usually look at closed source envs. But for you, yeah, I'll take a quick look at it and see if I can figure out what's wrong. Really is pretty cool. Sucks for RL that Mistral got Chris. It'd be awesome to have him doing RL stuff nowadays. I wonder what Chris would think of all the C stuff that I've been writing. I think he'd be down with it. It's like really just freaking simple ass C. I think he'd be down with it. Isn't he not a big RL fan? I don't know about that. I think he's just been doing language models at Minstrel with a bunch of guys that are like writing code 24/7 and having a good time getting a nice paycheck. I don't know if he like doesn't like RL anymore. I haven't heard that. Nice, it works. Well, yeah, RL's freaking cursed and broken because it hasn't had billions of dollars of engineering investment. But next best thing is going to be one PufferLib's worth of engineering investment. RL's going to work. 2025 here, it's going to be 10 times easier to get stuff up and running. Literally. I'm telling you, the end of 25, we're going to have RL 10 times easier to get working on new problems than it is now. So if it would take you, 10 hours to get something working on a new env, it's going to take you 1 hour. If it would take you 10 days, it will take you 1 day. Curriculum learning will be easier as well. You should do if you well, I know you have enough work to do already, but syllabus with Puffer native ends would be a cool thing. It's a little tricky because pipes are slow. Like on the scale of how fast our M's are, pipes are just too slow. So you'd probably have to do like a shared memory thing. Yeah, exactly. Like you can't just have like the pipe thing that you have is perfectly good for most RL environments, but at our scale, like when we're doing 1,000,000 steps per second, you can if you can still communicate stuff across processes and whatnot, but it's got to be in shared memory. It'd be pretty easy to bind for our like single process native M's though, because a lot of our M's are so fast, we literally just run them on the main process and still train at 1,000,000 steps per second. Design for fast prototyping. Yeah, wow. The goal is to do both, right, with Puffer. Like, if you look at our env wrappers and stuff's actually very, very simple, and it's fast. So we like to have our cake and eat it too. We're an elliptical encoder. What the hell? NetHack state embedding net. Models dot. Where the hell are models? Issues that curriculum learning algorithms have totally random interfaces. They're hard to optimize out of time. You need arbitrary data to answer to and from M's. Yeah, but we can do that. Like, that's not that hard to add. You have to have the data you have to put the data into an array. But if you do that, then it's not that bad. Because like what we do is we just, instead of having a pipe, right, you just have a shared memory buffer that you write to. So you're writing to a NumPy array in shared memory. The only thing that's obnoxious is like we'd have to add an extra thing into all the environments just to support the curriculum learning stuff. So there'd have to be pretty damn compelling evidence that like, this is the thing that's going to make RL sane and stable. I like curriculum learning, so I think it's definitely possible, but we need evidence. Really need to re-optimize it every time you add. Yeah, but the thing is, Ryan, like, you're in this mindset where there are a million algorithms constantly, and like we need to support all of them. We genuinely don't care. We just need like one good algorithm that works, and we just support the current best thing, and that's it. Right? Like Puffer doesn't have a million different algorithms, and it's not designed for a million different algorithms that have like arbitrary screwy things that they do. We have like a simple vec interface that works. We have no idea it works. Yeah, I mean, my approach to figuring out what works has just been make the experiments run like 10,000x faster, and then you kind of don't have to be very smart if you do that. You just run everything. Where are their models? I literally can't find their models. How does this import even work? Models dot. Huh? Source dot models as models. Oh, it's a file. I thought it'd be a folder. Me dumb. Okay. NetHack. I remember this prop shenanigans. This is the elliptical thingy. Why is there a full model on this elliptical thing? I do not understand this. State embeddings. So neither of these look like an elliptical. Well, neither of these look like the elliptical. Right? Neither of these look like the elliptical at all. So they have elliptical encoder elliptical encoder. Where's this thing? And then they define this. So this is this thing. I guess it's going to be in the loss function or something. Elliptical encoder. It's so hard to figure this shit out. I guess it's going to be in here. Is it compute policy gradient loss? Where's the reward? Intrinsic rewards plus bonus reward. Randomly, yeah, I've been reviewing like academic code bases all week, and this is the worst by far. This is just the worst. And that includes me having to deal with RL code. Well, the thing is, RLlib is they just have zero use, like they have zero checks on their API. So like if you use their API wrong at all, you just get like garbage internal messages 10 layers deep, and then it's slow. But the thing is, once you actually get the code written correctly, like it will run and not be that much code. It's completely opaque and you can't do anything with it, but like it runs. This is just like demonic. I have no idea what this is. Which is annoying because it looks like a pretty decent paper, but then it's just like you look at the code and it's holy hell. Okay, I guess, so this is inverse dynamics loss, right? And then they have elliptical encoder. Where does the intrinsic reward get computed? Bonus reward. I don't know where this gets rewarded. At least it's just a bunch of, yeah, I guess. But this is like maniacal because I can't find where they have the elliptical code. Is it in here? This is net, right? So I don't see elliptical in here. Where's the matrix stuff, right? There's supposed to be code on like low rank matrix stuff. All the curriculum on, that's good. That is what you should do. I literally can't find. Is this it? No. Like, where's the low rank matrix stuff? You have a whole habit of, yeah. But I need to find where they compute it. Oh yeah, Ryan, I wanted to ask you as well. So they have here, let me find this. I thought I did something kind of clever here. I thought I found something kind of clever with their math. So here's the paper. I think I found a nice improvement to it. So there's a major implementation quirk here where it's just going to be very, very difficult to implement this incorrectly. This is defined over episodes, meaning that you need episode bounds for this. You need like per agent episode bounds to compute this thing correctly. So what I was thinking of doing is instead, this is a strict sum, right? And they have an ablation that says if you sum over everything, like if you sum over all the episodes, it's really bad, non-episodic right here. So what if you made this exponentially decaying, right? What if I did like 0.9 times this thing? Like I just do like every time you get a new one of these, you do 0.9 times the old one plus 0.1 times the new one or something like that. I do like an exponentially decaying thing. And then you don't have to reset it. Does that work? Sounds interesting. Well, the thing is this, you can't do this. You just can't do this when you have variable episode length. Literally, where is their freaking logic? Where is their fancy? I literally can't find the piece of code that is the entire paper. I can't find it. Count. Literally, where's the piece of code? Okay, what's the torch inverse? Can I like search for inverse? KL inverse? Is this it? Inverse covariance. So this is it for habitat. So we have 1 over ridge on inverse covariance. Okay, here's the outer product buffers. I'm trying to think how I'm going to add this to Puffer. I'm trying to think how I'm going to add this to Puffer. So is it just like an extra state? Let me think. Look at the paper again. So you can almost just add this to the network, but not quite. I think it's an extra state that we have to add. Just like the LSTM state. Wait, C T minus 1. Given a feature encoding, wait, why does it only go to T minus 1? Hang on. Okay, so this is the previous state, basically. Wait, does this have to get differentiated through? Yeah, they use an inverse dynamics model for phi. But what was the alternative here? Oh, okay, so this is the simple way of producing it. Yeah, you just use the hidden layer, okay. So then if you do that, then this is a dot detach. I think this is not that bad. This is not that bad. So all I have to do is I have to add one state variable. The state variable is an inverted matrix. And then what's this update? Okay, so there is a way to do this. We'll start with the standard thing here. And this thing is apparently useful. Just joined, what paper is this? This is E3B, elliptical exploration via elliptical episode bonuses. They got this fancy function here that they just add as a reward. And this apparently helps. We're going to need to test this on a bunch of stuff. Say it helps generally. I mean, they test on a bunch of M's, not as many M's as I would like, but a bunch of M's. The thing is, exploration is always key, right? It's just that by default, we're doing it via, we're basically doing it via brute force initially. This is a generalization of counts-based exploration to continuous spaces. 2023, archived. I mean, it looks decent to me in the sense that, like, this is not that hard to compute. You only have to add, like, two small things to your algorithm. Continuous, no, it's not continuous action spaces specific. It'll work for anything. It'll work for whatever. Well, it won't, right? You never know with these papers. Half the time they only work on the experiments that they were done for here, but I don't know, this probably does something. We'll see how annoying this thing is to compute. I think it shouldn't be that bad. I'm gonna go grab a quick. I got a meeting in 30 minutes. They have reference code? Yeah, it's terrible reference code, but they have it. It's like god-awful reference code, but they have it. It's on Facebook Research /E3B. So I'm probably going to start implementing this later tonight. I got a 3 p.m. meeting, so probably, and I got to make a couple quick calls, so probably after that. So yeah, let me do that now. What I'm going to go do, I'm going to grab a quick snack. I'm going to make a couple calls I got to make. And then we'll come back later and I'll start on this. Also, we made, Captain, I made a huge amount of progress on carbs. I think I figured out why it's not working as well as it should be. That's going to take me a couple days of work, but we're going to have way better hyperparameter sweeps. So I figured that out today as well. What's the problem? Pretty much the thing that I said where they're transforming parameters into they're applying bad transformations to the parameters and applying bad sampling, basically. So they have a really good algorithm, but they're just doing their data transforms and sampling wrong. I mean, it makes sense that they are. Their code is like horribly overcomplicated there as well. In fact, I think that there are two projects that I want just for Puffer. One is I want a much cleaned up and simpler version of carbs that matches or exceeds the original. And then I want the same for Vox 2D. So those are two major projects for people to look at. I'm probably going to do the carbs one myself because it's kind of technical, unless anybody's really wants to look at it. Seeing the code you're talking about didn't grok it. Didn't try to see if it was correct. Yeah. I don't know why your message just didn't show up on the stream though. I see it in the chat. That's weird. Yeah, it's a weird plugin thing. Okay, I'm gonna go. I only got a half hour to do some stuff, so I'm gonna go do some stuff, and I will be back later in the afternoon. Thanks for tuning in, folks. If you're interested in getting involved or learning more about Puffer, puffer.ai, GitHub, start, helps us out a ton. Discord, discord.gg/puffer. Get involved here. And you can also follow me on X, where I post all sorts of RL stuff. Thanks.